Hello, good morning to you, and welcome to another very exciting edition of our 1% Engineering series. For today, we're going to talk about piping stress analysis, and in the piping stress analysis, we're going to talk about primary stresses. We're going to look at it from the CISA 2, using CISA 2 as a tool. CISA 2 actually from here. CISA 2 actually stands for Computer Aided Engineering, Stress Analysis and Routing. So we're going to look at primary stress analysis today, and then we're going to see the factors, the two basic factors that affect primary stresses. We're going to see weight and pressure. Those are the two basic factors. Pressure of the fluid actually inside the pipe. All right, so this is the model we'll be using today to demonstrate primary stresses, and we're going to model the system. After modeling the system, we're going to impose the boundary conditions on it, that is its temperature and its pressure, operating conditions actually, and then this pipe material given as ASTM A106 grade B already given. We'll have a fluid density, and then we'll have a flange material of ASTM A105. All right, we're going to see how to apply this in CISA 2 and resolve primary stresses. All right, I open up my CISA 2 and then I go to new. I want to create, let's call this primary stresses, or let's say primary stress, right? And then I say okay to this. My units are in millimeters, so hopefully I get this in millimeters, already in millimeters, but if it was not in millimeters, I will change the units. Probably in the subsequent videos we will see that, but for now it's already in SI millimeter units, so we'll go ahead and do that. Okay, so we're waiting for the piping input spreadsheet to appear. All right, here it is. So for us here now, we're going to go straight to modeling this system, and then the first thing we're going to model here is a flange, right? A flange. There's a flange connection between the piping system and the equipment nozzle, which is going to be represented here as an anchor. We'll get to that. We're going to select the flange class. So have a flange table here for us. So this is for ASTM A105. Remember, if you want to select a flange, you want to work with the MOC of the flange, and then the pressure and the temperature. So, and it's actually important to know that the pressure values here inside of this table, they are in PSIG, as you can see from here, and then the temperature values are in Fahrenheit. Okay, so if you look at our piping model, it is 300 degrees Celsius and then 8763 kilopascal. All right, so going back to our table, 300 degrees Celsius corresponds to 572 degrees Fahrenheit. So 572 degrees Fahrenheit is, there is no interpolation in this table actually. So 500 degrees Fahrenheit corresponds to 572 degrees Fahrenheit is more than 500, so but it's less than 600. I'm going to use the next temperature, which is immediately higher than the temperature we are looking at. Remember I said there is no interpolation in this table. All right, so we have 600. I'm working use of 600 because my temperature value in degree Fahrenheit is 572. All right, so 8763 kilopascal of pressure corresponds to 1270 point some fractions of some fractions in PSIG, but this particular value is greater than 140. Pressure is greater than that, it's greater than this, it's greater than this, it's greater than this, but not greater than this. So I'm going to also work with this. So you see the intersection of 600, right, and of this pressure, I will read the value up, and then I have class, okay, sorry, it should be this rather. So I have class 900, right? So I have class 900 flange. So if I go back to my piping model, to my piping input spreadsheet, I'm going to select a class, a flange class here of 900. But for now, we already know that a flange is A105. That is what a flange is. So we have to specify the material, and then we have to see what size of pipe diameter. We can see it's already 6 inches. You can see that from here. It's 6 inches NS nominal pipe size. Okay. For the schedule, we're going to design a system from the scratch, so I'm going to exaggerate this in a bit, such that we're going to see how hoop stress will fill the system if I do not give a minimum thickness that can withstand the pressure in the system. All right, so let's go for 5S. We'll see these things. 5S, I think this is the minimum schedule we have, and then that is for that, and then temperature here is 300 degrees C, and then we have a pressure of 8763, right? 8763. So if I go back to my model, I go to flange, I will find valve. I will go to flange here, and then because I'm going to connect the pipe immediately after it, I will say no flange, and then I go to class 900. So I will say okay to this. So I have this appearing in this direction, but we know this from this model, it should be facing upwards, right, in the vertical direction, which is in the Y direction. All right, so but I'm going to have a pipe of short pipe of 500 millimeters, which stops at the center of the adjoining elbow. All right, so we'll go back to this, but we're going to cut this from here. We're going to cut this value and paste it here. All right, so we have this value pasted here, and then it is facing in this direction. This is a class 900 flange. All right, so I'll go to continue, and then I will not forget, because the next element is a pipe, and the piping material is different. A106 grade B, so I'm changing that to A106 grade B at this point. And then it is 500 millimeters, I'll say 500, and then there is a bend attached to this 500 millimeters. All right, so the next element is, if we see from here, the next element is 5000 millimeters, and it stops at the center of the next elbow. Okay, so I go 500 millimeters, and that is in the negative Z direction. So I will say negative 5000 millimeters, and then I'm going to double click a bend. The next element is 8000, and it's in the negative Y, right? It's 8000 and it's in the negative Y. So I'll say 8000 to this. The next element is, we'll see from here again. Next element is 6500, and it's in the negative Z, right? So again, there's a bend here. At the end of this element, I say continue, and in the negative Z, we say 6500. 6500, there is also a bend at that point. The next element is, find that now. The next element is 3300, and then it is in the X direction. So 3300, and it's in the X direction. The next element, I think, is 7700. Let's confirm that. Is 7700, and then 750. This is in the Z direction, and then this is going to be in the Y direction. Okay, so I say continue to this. I say continue to this, and then this is in the Z direction, 7700 in the negative Z. Sorry, 7700, and then I have a bend there, and the last is in the negative Y, 750. 750 in the negative Y. So I go continue, and then I add my flange of class 900 again. So no flange, class 900, okay, at the end of this other element. So you can see how simple it is to actually model this and then come up with the exact same model we have there. So of course you want your model to be correct, because if your model is not correct, if there's any deviation in modeling from the actual system, of course, you know, you're going to be getting a solution that does not represent what you're trying to model, right? Or what you're trying, the real problem you're trying to solve. All right, so what I would do here is I would simulate the anchor. I'm going to model the anchor, which will represent the equipment nozzle, right? Because I'm not doing equipment nozzle analysis here, so there will be no need putting an equipment nozzle here, right? So I'm only interested in the integrity of this particular piping system. So I have an anchor there, which represents the equipment nozzle. So next, I would need to get the I will need to go to the first element. So first element, I double click restrain, and then for your restrain, you also need an anchor at node 10, which is what we have right here, right? So you have your anchor at this point. All right, so this particular model has been completed. It's a very simple model, very straightforward, no complexity at all. And then I will just say, I want to start the analysis now proper. So I will say run this analysis. Okay, we have our results, our reports sheets. So our static output processor, and then from this colors, we can already see that there is a problem in the sustained case. Now, the first one is the OPE case, which is a combination of weight, temperature, and pressure. You have temperature 1 because we only have one temperature of 300 degrees Celsius. We have pressure 1 because we only have one pressure of 8763 kilopascal. But you can have more temperatures and pressures if your system requires that, or if your system sees that. Okay, so for here, sustained, it is the weight and the pressure combination we're actually looking at. Now, this particular one is actually called the sustained case, or the primary case, or the cold case. So you can already see that there is a problem with the cold case of this material, or of this piping system rather. So there is a problem which definitely came from either the pressure, either the weight, or the pressure. So this is the expansion case. The expansion case talks about the temperature case, right? In subsequent videos, we'll look at the expansion case. But for now, let's pay attention to this man where we have failure here. So when I click on that, I would go to my stresses. So I want to see the primary stresses, and then I will say OK to this. View reports. So I'm waiting for my reports. Okay, my report is out, and then you could see license to this, stress report, stresses on elements, case 2, which is a sustained case. So I'm going to look at here, it says code stress check failed, right? Now what has failed the system is actually the weight or the pressure, or a combination of both, right? So we're going to find out shortly what actually failed the system. So the highest ratio, the highest stresses here are actually in this part of this table, in this part of this report. So the ratio here is 253.9, and that is the highest ratio, code ratio, at 253.9 at node 28. So we have 253.9 at node 28. The actual stress is 318,803.5 at, of course, in kilopascal, at an allowable, over an allowable of 125,539.7. So if I say this divided by this multiplied by 100, I'm going to get at 253.9. So this already exceeds 100% of this particular piping system. So you have exceeded your allowable, and that is why it has failed. But let me say this, primary stress, whenever there is a failure in the primary stress category, it does not actually mean that the system has actually fractured. Let's go back to our, let's see our ductile stress strain curve, right? Material stress strain curve. So if you look at this particular curve, you will see that your primary stress actually exists within this linear region, right? It exists within the sorry about that. So it exists within the linear region of the stress strain curve, right? So, and it is bounded by the yield strength. So it means that for primary stress, it is actually forbidden. ASME BT 1.3 will also tell you that it is forbidden for yielding to occur due to primary stresses. So we do not want yielding to occur, because when yielding occurs, it means that the highest limit of the primary of the allowable stress has been exceeded, and most times it's just a fraction of your yield strength, right? So whenever I have a stress value, an applied stress value that exceeds my yield strength, I'm going to have a primary stress failure because yielding has occurred. So it does not mean actually that I've gotten to the fracture point. No, you may not be close to the fracture point, but any value that is slightly greater than the yield strength, or a fraction of the yield strength as seen from the code, will report failure, right? So it will report failure. So the failure we're having now does not necessarily mean that we have fractured, that the pipe will fracture. It only means that the pipe is actually, the applied stress has caused the pipe to actually yield, right? Okay, so that is for that. The next thing we'll do here is we're going to find out which particular stress has actually failed the system. And if you see, my code stress is this, but if you look at your axial stress and you look at your bending stress, torsion stress, and then your hoop stress, right? Do not pay much attention to the 3D, to the max stress intensity rather. So I want to pay attention to axial, bending, torsion, and hoop. If you look at these values, you will see that the highest contributor to this core stress failure you have here, to the core stress you have here, is actually your hoop stress, right? Your hoop stress is very high. 257 is already greater than your allowable stress of 125, right? So whenever hoop stress fails the system, it only points to an insufficient thickness, right? Which is insufficient to contain the pressure, the fluid pressure. So remember when we are doing this design, we started from the least schedule, right? From the least schedule, and then we just wanted to exaggerate this and to show you that, okay, these are the likely things that are going to fail your system. So we could see that the problem here is pressure, but not particularly pressure, because this pressure is what the system wants to work with. So it just tells you that pressure in relation to the thickness is very high, right? So the pressure over thickness ratio is very high. So what we're going to do here is I want to reduce this ratio of pressure over the thickness. So what we'll do is I want to increase the thickness, and by increasing the thickness for us here, we are going to work on the schedule. So I just close that, and then I'll go back to the piping input. So for this piping input, waiting for the piping input to appear. So for this piping input, what I will just do here is I will advise in your own practice, you could be going gradually and seeing which schedule actually is minimum for you. But for trying to keep this video, for me to try and keep this video short, not make it too much lengthy, I am going to just go straight to schedule 40, right? So schedule 40 corresponds to 7.1120 millimeters of thickness, right? For a pipe thickness of for a pipe size of 6 inches NS, right? So let's see, and remember I have changed this thickness, this schedule value at node 10 to node 20. So everything forward from this, everything subsequently will actually change to this particular schedule number or this particular thickness. So if you go forward, you see that all values, right, are in 7.1120 millimeters. All right, so let's see, we have already played with the schedule. Let's see whether we're going to reduce whether there's any drop in the percentage stress, or possibly whether the system has passed. Also, okay, as you can see from here, we still have a failure in the primary stress sustained or primary stress. So if I say view the stress report, let's see whether there is any drop in the percentage stress, right? Okay, so if we go down, you see that I think we had about 250 something percent at this point before now, but it has reduced to 214%, right? If you look at your code stress, it still appears very high, right? So who is the highest contributor this time? It is no longer your hoop stress. Your hoop stress value has dropped below 100,000. So this is fine, but your bending stress is quite high, right? Your bending stress value is quite high. So whenever bending occurs in a system, we know that it must come with some kind of displacement, right? It moves the piping system away from its original center. All right, so or from its particular equilibrium position. So let's see the displacement report of the sustained case. So if I hit sustained displacement report and then I go to view report, okay, in the view report, you will see that in my x direction, this might the x, the y, the z, these are linear displacements. This is rotation about x, rotation about y, rotation about z. So, but if you pay attention very closely, you will see that at this point, right, close to your node, from node 38, we are beginning to have very high and significant displacement in the y, right? So even though we still have some in the X and in the Z, right? But they are not as compared to those in the Y. So it's very possible that displacement in the Y is actually the reason why we're having such displacement in the X and in the Z. So if you go down for more, you will see that I have very high displacements, right? Up to node 70, right? And then before it reduces further again at 80, 78, and then downwards. All right, so you see that from node 38, right? From node 38 here, from node 38 in the Y direction down to node 70, I have displacements, high displacements in the Y, and they are negative displacements. When we have negative displacement, then there should be negative forces causing the negative displacement, right, in that particular direction. All right, so because everything will move in the direction of the force applying, of the force being applied on it. So if I close this and I go back to my piping input, go back to my piping input, opening up. Okay, if you go back to your piping input, I'm going to select this element. I know somewhere here, if we display the node numbers, we have, this is at 40, and then 38 is somewhere very close to 40 here. So, but if you see what is happening here, 30 is almost difficult or impossible for me to actually put a support at this point, right? Of course, this depends on what are the other existing equipment and elements very close to this pipe. But for us here now, I want to concentrate just on what we have here. So at 38, I already have displacement up to this point, 70. So what I'm going to do, if you look at this pipe, it looks very long, right? This is a riser. So it looks very, this is the, I think this should be the longest part of this piping system. All right, so I'm going to support this pipe at this point, right? Since this point is trying to move downwards. So I'm going to support this particular vertical section of this piping system, support it here, and then place another support here, and then place another support here, right? And then see whether we would have the displacement reduced and the bending stress actually that is causing failure eliminated. All right, so what we'll do here is I will hit this element, this one, select element, and then for select elements, let me remove your display node numbers. So I will click here. So it takes me to node to element 50 to 60, right? So this particular one here represents element 50 to 60. But of course, you know, I cannot just add a support on the on an elbow. So what I'm going to do is I'm going to break this. I'll hit break here, and then between 50 and 60, I want a new node number called 55. And then let's say I want it 350 millimeters away from node 50, just somewhere not too far from node 50. I will say okay to this, right? And then if you see here, I have node 55. If I display the node numbers again, you see I have node 55. So it is at node 55 that I want to attach a restraint, but this time it's not going to be an anchor, it's going to be a plus Y support, because I have negative forces causing negative displacements there in the Y direction. Therefore, I need to counter these forces. So I'm going to work with a positive Y support, right? I click on the positive Y support. Now what I should do is that I should size this particular support and then add a stiffness value, but for the sake of this video, we will do that subsequently. I will just leave this to have his default value, right? So, and you could see that I have my vertical support at this point. Okay, so next for us is somewhere here. Sorry. All right, so somewhere there 60 to 70 I break. I want it 65, and then I could say let it be 350 millimeters away from 60. I say okay to this, and then I would double click on this restraint, and then I want to add a plus Y support. You have your plus Y support here, and then on this final one I want to break again, and then I want a new node number 75. And then at this point, I want it 350 away from 70, and then I will double click restrain and add a plus Y support. Okay, so I think I have these three supports in these locations, right? So I'm going to run this analysis again and see what the issue is whether we have been able to solve this problem. So as you can see, this particular the primary problem we had been resolved. The first time when we had a hoop stress problem, it was just due to pressure, right? And insufficient thickness. Pressure thickness ratio was very, very high. So we needed to reduce it. Pressure over minimum thickness was very high. So we needed to reduce it by increasing our minimum thickness. We did that, and you saw that the hoop stress value was reduced, but it still failed under bending, even though we had an overall decrease in the cold stress percentage. And for the bending stress, we dealt with the weight problem, because when bending occurs, most times, even though there could be some pressure contributions, but most times it happens due to weight, right? So we now added support, and you could see that the piping system has been solved. The problem with the piping system has been solved. So if I go back to stresses, primary stresses, and view reports, you would see that I no longer have failure as reported, as you can see from the colors, from the color here. It's no longer red. So it says code stress check passed, right? And if you see the code stress here, we have it at 45.3, very low, right? Which is not too low, but very okay, right? So you could see that this is how to solve primary stress problems. Primary stress problems, just a recap, is due to weight and pressure. Nothing more than that. So you could see how we started with a schedule 5S, and then which gave us a thickness value of about 2.7 something millimeters. So you would see that if I increase this value excessively, the thickness value, which is this one, if I increase this value excessively, I could start introducing or having a weight kind of problem, right? Again, I have to reiterate, the first problem of every piping system is its own weight, right? So even though we solved the pressure problem, you discover that we still had weight to contend with, right? A piping system will suffer first from its own weight. All right, take care and have a wonderful day ahead. This is all I have to show you for today on primary stresses. If you have any issues, any confusion anywhere on what I've just done today, let me know, and we'll resolve that together. Take care and have a good day.